The Mitsubishi A6M mechanics at Vladivostok Airfield stopped their work when they heard it. The sound was wrong. Not the familiar drone of Soviet fighters returning from patrol, but something deeper, heavier, a rumble that made the ground vibrate beneath their feet. It was July 20th, 1944, and what taxied onto that remote Soviet airfield would change the course of the Cold War before that war had even begun. The aircraft was enormous. Wingspan 141 feet, 4 massive radial engines, silver aluminum skin that gleamed even under the overcast sky. An American Boeing B-29 Superfortress, serial number 42-24754, call sign Ramp Tramp. The crew had bombed the Showa Steel Works in Manchuria and couldn't make it back to their base in China. Fuel exhaustion, engine trouble, battle damage. They had violated Soviet airspace because the alternative was ditching in the Sea of Japan. The Soviet guards who surrounded the aircraft as it shut down engines had no idea they were looking at the most expensive military project in American history. More costly than the Manhattan Project, more technologically advanced than anything flying in Soviet skies. The crew expected to be interned briefly, then returned home. The Soviets and Americans were allies, after all, fighting the same war against the same enemies. They were wrong. Within hours, orders came from Moscow. The aircraft would not be returned. The crew would be interned indefinitely, and every rivet, every wire, every technological innovation in that airplane would be measured, documented, and copied. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But this wasn't the first B-29 to land in Soviet territory. On August 20th, 1944, another Superfortress, this one badly damaged, had crash-landed east of Khabarovsk after a raid on Japan. The crew bailed out. The aircraft was destroyed, but enough remained for Soviet engineers to begin their examination. Then came 2 more emergency landings in November. By the end of 1944, the Soviet Union possessed 3 intact B-29s and the wreckage of a 4th. Joseph Stalin saw opportunity where others saw diplomatic complication. The Soviet Union had no strategic bomber, nothing that could reach distant targets and return, nothing that could carry the atomic weapons Soviet scientists were racing to develop. The Petlyakov P-8, their only 4-engine heavy bomber, had been designed in the 1930s. Only 93 had been built during the entire war. It was obsolete before the war even started. Stalin had watched with envy as American B-29s struck Japan from bases thousands of miles away. He had repeatedly asked President Roosevelt to provide B-29s under the Lend-Lease program. The Americans had sent the Soviets $11 billion in materials during the war, over 400,000 jeeps and trucks, 12,000 armored vehicles, 11,000 aircraft, nearly 2,000 locomotives, but they refused to send heavy bombers. The B-29 was too valuable, too advanced, too secret. Now Stalin had 3 of them, and he intended to build more, many more. In June 1945, Stalin summoned Andrei Nikolaevich Tupolev to the Kremlin. Tupolev was the Soviet Union's most accomplished aircraft designer. He had survived Stalin's purges in the 1930s, spending time in a prison design bureau before being rehabilitated. He knew what happened to people who disappointed Stalin. He knew what was expected when Stalin gave an order. The order was simple and terrifying. Copy the B-29, exactly, every detail, every part, every system. Have it ready for production as quickly as possible. Not an improved version, not a Soviet interpretation, an exact copy. Tupolev tried to argue that Soviet engineers could improve on the American design. Stalin cut him off. The Americans had spent billions of dollars and years of development creating this aircraft. They had solved problems Soviet engineers didn't even know existed. Copy it. Exactly. Tupolev understood. This wasn't about pride. It was about survival. The Boeing B-29 Superfortress represented a revolution in aviation technology. When the first prototype flew on September 21, 1942, It incorporated more innovations in a single aircraft than any previous military program. The Army Air Forces had ordered 1,664 aircraft before the prototype ever left the ground. The gamble cost $3 billion, equivalent to $49 billion in today's currency. The aircraft's most significant innovation was its pressurization system. Developed by WWII Research Manufacturing Company, it allowed the B-29 to operate at altitudes above 30,000 feet while the crew worked in shirt-sleeve comfort. The system used compressed air from superchargers on the two inboard engines, delivered through ducts into three separate pressurized compartments. The forward compartment housed the bombardier, pilot, co-pilot, flight engineer, navigator, and radio operator. The rear compartment contained the central fire control gunner, left and right gunners, and radar operator. The tail gunner worked in his own isolated pressurized section. From sea level to 8,000 feet altitude, the system simply provided ventilation. From 8,000 feet to 30,000 feet, automatic regulators maintained a constant 8,000-foot pressure inside the cabins. Above 30,000 feet, the internal pressure gradually increased with altitude. At 34,000 feet, the cabin pressure equaled 10,000 feet. The crew could patch bullet holes during flight using techniques Boeing had developed specifically for combat damage repair. This pressurization solved two critical problems that had plagued high-altitude flight. The first was anoxia, the medical term for oxygen starvation. At 25,000 feet, atmospheric pressure drops to 1/3 of sea level. Blood cannot absorb sufficient oxygen. Pilots become confused, sluggish, unable to make decisions. On longer missions, oxygen masks were exhausting to use and reduced crew effectiveness. The second problem was aeroembolism, also called the bends. Nitrogen dissolved in blood at sea level pressure releases as bubbles at high altitude, blocking blood vessels and causing severe pain and permanent damage. The B-29's fire control system was equally revolutionary. General Electric designed a remote-controlled gun turret system that networked 4 turrets together through analog computers. Instead of gunners sitting exposed in freezing wind at 30,000 feet, they worked inside heated, pressurized compartments, operating turrets by remote control. The computers corrected for airspeed, target speed, lead angle, gravity, temperature, barrel wear, and humidity. The system gave the 50 caliber machine guns an effective range of 1,000 yards, double the range of manually aimed guns on the B-17 Flying Fortress. The Wright R3 350 duplex Cyclone engines were the most powerful piston engines flying when the B-29 entered service. 18 cylinders arranged in 2 rows, 2,200 horsepower each at 1,800 revolutions per minute. Twin General Electric turbo superchargers on each engine maintained maximum power up to 30,000 feet altitude. The engines burned 100-octane aviation gasoline at a rate that required the aircraft to carry 9,363 gallons of fuel for long-range missions. But these engines were also problematic. The cylinders were spaced too closely for efficient cooling. Lubrication of the upper cylinders was insufficient. The reduction drive was prone to failure. The carburetor produced inefficient fuel mixture distribution. All these factors contributed to engine overheating and fires. The extensive use of magnesium in the crankshaft to save weight meant that when engines caught fire, they burned with white-hot intensity that could spread to wing spars within seconds. The grim joke among B-29 crews was that they were being killed more by Curtiss-Wright, the engine manufacturer, than by the Japanese. The airframe itself was massive. 99 feet long, 29 feet 7 inches tall, empty weight of 74,500 pounds, maximum takeoff weight of 140,000 pounds. The fuselage used circular cross-sections for structural strength under pressurization. A perfect circle maintains its shape under pressure better than any other configuration. Boeing had learned this lesson developing the 307 Stratoliner, the first pressurized commercial airliner, in 1935. When Soviet engineers first entered the intact B-29s at Vladivostok and Central Airfield in Moscow, they faced a technological gap that seemed impossible to bridge. Everything about the American bomber was beyond Soviet manufacturing capability. The lightweight aluminum alloys, the precision machining, the electrical systems, the hydraulics, the instruments, even the rivet patterns and skin joints were specified to reduce drag in ways Soviet aircraft designers had never attempted. The Soviet Union used the metric system. Every measurement on the B-29 was in inches, feet, and pounds. Sheet aluminum, matching American gauge thicknesses, was unavailable in Soviet industry. The corresponding metric gauge metal was different thicknesses. Either Soviet engineers would need to recreate the entire American measurement system in their factories, or they would need to extensively re-engineer every component to use available Soviet materials while maintaining structural integrity. Tupolev assembled a team of 900 factories and research institutes. They would dismantle one aircraft completely, measuring and cataloguing each of the 105,000 parts. A second aircraft would serve as a reference standard for cross-checking measurements. The third would be used for flight testing and pilot training. The wreckage of the fourth provided additional components for study. The engineers discovered that the 3 intact aircraft were actually different models from different production lines. One was a Boeing Wichita-5-BW, 2 were Boeing Wichita-15-BWs. The wreckage was from a Boeing Renton-1-BN. Only one of the 4 had de-icing boots, as would eventually be used on the Soviet version. Every small difference had to be documented and decisions made about which configuration to copy. Stalin's deadline was brutal. The design work had to be finished in 1 year. By the end of the second year, Soviet industry had to produce 20 aircraft ready for state acceptance trials. Tupolev knew this timeline was nearly impossible. The technical challenges were immense. The political pressure was worse. The engineers began with the systems they could see and measure: the pressurization ducts, the oxygen system, the fuel tanks, the hydraulic lines, the electrical wiring, which totaled more than 10 miles per aircraft. Each wire had to be traced, measured, documented. The gauge had to be determined, the insulation type identified, the routing mapped. Then came the systems they couldn't easily measure: the metallurgy of the aluminum alloys, the heat treatment processes, the chemical composition of rubber seals and gaskets, the exact formulation of hydraulic fluids. The Americans had developed materials and processes specifically for the B-29 that didn't exist in Soviet industry. Some materials simply weren't available in the Soviet Union and would need to be invented from scratch. The engines presented perhaps the greatest challenge. The Wright R-350 was assigned to the Shvetsov Design Bureau to copy. Every cylinder had to be measured, every valve, every bearing, every seal. The superchargers were complex pieces of precision engineering. The propellers were equally sophisticated, with variable pitch mechanisms that had to be perfectly balanced. The fire control system required Soviet engineers to understand American analog computer technology. The General Electric gun computers took inputs from multiple sensors, performed ballistic calculations, and output firing solutions to remote turrets, all mechanically using gears, cams, and linkages. Soviet engineers had nothing comparable. They would need to reverse engineer not just the hardware, but the underlying mathematics and engineering principles. The Norden bomb sight, one of America's most closely guarded military secrets, was installed in one of the captured aircraft. Soviet engineers examined it carefully, documenting its mechanisms. This alone was an intelligence coup worth the entire B-29 acquisition. By early 1945, the full scope of the challenge was clear. Tupolev's team had created 105,000 engineering drawings. They had identified materials that didn't exist in Soviet industry. They had discovered manufacturing processes Soviet factories couldn't perform. They had found precision requirements Soviet machine tools couldn't meet, and they had less than 2 years to solve all of it. The pressurization system alone threatened to derail the entire project. Garrett I Research had designed a sophisticated automatic control system using regulators that maintained precise cabin pressure across a wide altitude range. The system required airtight seals at every penetration point in the fuselage, door frames, window frames, Access panels, gun turret mountings. Every location where wires, cables, control rods passed through the pressure hull. Soviet engineers measured the seal tolerances, gaps of thousandths of an inch. The rubber compounds used in American seals were different from anything Soviet industry produced. American rubber maintained flexibility at -40 degrees Fahrenheit and didn't degrade in contact with aviation fuel, hydraulic fluid, or lubricating oil. Soviet rubber compounds couldn't meet all these requirements simultaneously. The aluminum alloys presented equally difficult challenges. American metallurgists had developed specific alloys for different parts of the airframe: high-strength aluminum for structural members, softer, more formable aluminum for skin panels, corrosion-resistant aluminum for components exposed to weather. Each alloy had different heat treatment requirements and different working properties. Soviet aluminum came in different thicknesses because of the metric versus imperial measurement systems. Using thicker Soviet aluminum added weight. Using thinner material, compromised strength. The engineers had to recalculate stress loads for every structural component, adjusting thickness to maintain strength while minimizing weight penalty. They reduced Soviet safety margins to avoid complete redesign. It was a calculated risk driven by Stalin's impossible timeline. The electrical system contained more than 800,000 individual connections per aircraft. Every connection had to be disassembled, catalogued, and understood. American electrical connectors used standardized fittings Soviet factories didn't produce. Soviet engineers would need to create new connector designs or find ways to adapt existing Soviet electrical components. The Shvetsov Design Bureau struggled with the Wright R3-350 engine. The 18-cylinder twin-row radial was more complex than any engine Soviet industry had mass-produced. The valve train, the supercharger drive system, the reduction gearbox, the fuel injection system, every component had to be measured with precision Soviet machine tools could barely achieve. American engineers had balanced the Wright engine crankshaft to tolerances measured in fractions of ounces. Any imbalance caused vibration. Vibration caused fatigue failures. Fatigue failures caused catastrophic engine destruction at altitude. Soviet machining equipment couldn't consistently hold the required tolerances. Engineers would need to hand balance each crankshaft, a time-consuming process that would limit production rates. The propellers were four-bladed Hamilton Standard constant-speed units with hydraulic pitch control. The blades were hollow, saving weight while maintaining strength. Soviet engineers had experience with simpler three-bladed propellers on earlier aircraft, but the B-29 propellers incorporated features they'd never attempted: the hollow blade construction, the complex pitch change mechanism, the counterweight system, the fine pitch stops and coarse pitch stops. Tupolev assigned the propeller reverse engineering to a separate design bureau. They dismantled one propeller completely, documenting every part. The blade cross-sections, the spar construction, the hydraulic cylinder dimensions, the governor mechanism settings. They discovered American engineers had used wood laminations in some internal structures, bonded with adhesives Soviet industry didn't manufacture. The remote-controlled gun turrets required Soviet engineers to master entirely new technology: the electric motors that rotated the turrets, the cell-syn motors that transmitted position data from the gunner's sight to the turret, the analog computer that calculated lead angles and deflection, the mechanical linkages that aimed the guns based on computer outputs. General Electric had designed the fire control system as an integrated whole: the gunner's sight, the computer, the turret drives, the gun charging mechanisms. Everything worked together through electrical and mechanical connections. Soviet engineers couldn't simply copy individual components. They had to understand the entire system and how each part interacted with every other part. By mid-1945, Tupolev's team had identified over 900 separate manufacturing problems, materials that didn't exist, processes Soviet factories couldn't perform, tolerances Soviet machines couldn't hold, tools that would need to be designed and built before production could begin. Each problem had a solution, but every solution required time and resources the Soviet Union barely had. Leonid Kerber, one of Tupolev's senior engineers on the project, later described the atmosphere of fear that pervaded the design bureau. Tupolev had survived Stalin's purges once by producing results from a prison design bureau. He knew failure meant death. Not just his own death, but the deaths of his entire team. Stalin had made that clear. Lavrenti Beria, chief of Stalin's secret police, visited the design bureau regularly to emphasize the consequences of missing deadlines. Tupolev insisted on copying every detail, no matter how seemingly insignificant. Engineers discovered a small hole in the aircraft skin that appeared to serve no purpose. They debated whether to include it in the Soviet version. Tupolev ordered it, copied exactly. The Americans had put it there for a reason, even if Soviet engineers couldn't determine what that reason was. Later analysis revealed it was a manufacturing artifact, a mistake that had been copied into production aircraft and never corrected. But Tupolev couldn't risk omitting it. What if it served some crucial function Soviet engineers didn't understand? Rumors circulated among the engineering teams that even flak damage on the wings was being carefully measured and reproduced. The stories were exaggerated, but they reflected a fundamental truth. Tupolev was terrified of deviating from the American design. Better to copy a mistake than risk Stalin's wrath by attempting improvements that might introduce unforeseen problems. The engineers worked 18-hour days, 7 days a week. Design bureaus across the Soviet Union contributed expertise. The Central Aerohydrodynamics Institute studied the wing design. The Aero Engine Institute analyzed the right engines. Universities assigned their best aeronautical engineering students to support the project. Entire factories were retooled to produce components for the Soviet Superfortress. Progress reports went to Stalin weekly. Tupolev presented each report personally, explaining difficulties and proposing solutions. Stalin listened, asked questions, and set new deadlines that seemed designed to be barely achievable. The message was clear: work faster, accept no excuses, produce results. The aluminum shortage became critical in late 1945. Soviet industry produced aluminum, but not in quantities sufficient for mass production of large aircraft, while maintaining production of fighters, tanks, and other weapons. The government redirected aluminum from civilian uses: cooking pots, electrical wire, building materials. Everything went to aircraft production. The machine tool shortage was equally severe. Precision machining equipment was concentrated in factories that had been evacuated east of the Ural Mountains during the German invasion. These factories were already operating at capacity, producing weapons for the war effort. Adding B-29 component production meant reducing production of something else. Stalin made the decision. Strategic bomber development took priority over everything except immediate frontline needs. Soviet engineers discovered that American workers had wired some systems incorrectly on the captured B-29s. The errors had been corrected in the field with modification kits. Soviet engineers had to determine which wiring represented original factory configuration and which represented field modifications. They couldn't simply copy what they saw. They had to understand American production procedures and field modification practices. The Americans had used specialized tooling to produce B-29 components: massive presses to form aluminum skin panels, jigs to hold fuselage sections during assembly, fixtures to align wings during attachment. Soviet factories would need equivalent tooling, but the Americans obviously weren't going to provide manufacturing equipment. Soviet tool designers had to create their own versions based on examining the finished aircraft and reverse engineering the production processes. Some innovations were purely American and couldn't be replicated. The Americans had plexiglass nose sections molded in single pieces using processes Soviet industry couldn't duplicate. Soviet engineers had to design multi-piece nose sections using flat or simply curved panels that could be manufactured with available equipment. This added weight and increased drag, but it was the only feasible solution. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The pressure on workers throughout the Soviet industrial system was immense. Factories received quotas for components. Miss the quota, face consequences. Deliver defective parts, face harsher consequences. Quality inspectors rejected components that didn't meet specifications, but specifications written from American measurements often required precision Soviet manufacturing couldn't consistently achieve. On May 19, 1947, test pilot Nikolai Stepanovich Rybko climbed into the cockpit of the first Soviet-built copy of the B-29. The aircraft was designated Tu-4. It sat on the runway at the flight test center outside Moscow, silver aluminum skin gleaming in the spring sunlight. 22 months had passed since Stalin issued his order to Tupolev. The deadline had been impossibly too tight. Somehow, Tupolev's team had met it. Rybko was one of the Soviet Union's most experienced test pilots, decorated, skilled, trusted. He knew this flight would determine the fate of thousands of people who had worked on the project. If the aircraft flew successfully, they would be heroes of socialist labor. If it failed, many would disappear into the Gulag system. Some would face firing squads. He ran through the checklist, calling out items to his flight engineer: fuel quantity, oil pressure, hydraulic pressure, electrical systems, flight controls. Everything had to be perfect. The 4 Shvetsov A-6, 73 engines, Soviet copies of the Wright R3, 350, idled smoothly. Engineers had tested these engines for hundreds of hours on test stands, working out problems, adjusting tolerances, replacing parts that failed. Rybko advanced the throttles. The engines roared to full power. 2,200 horsepower per engine, 8,800 horsepower total, shaking, the massive airframe. He released the brakes. The Tu-4 began rolling, slowly at first, then faster as speed built. At 130 miles per hour, Rybko eased back on the control yoke. The nose lifted. The main wheels left the runway. The Soviet Union's first strategic bomber climbed into Soviet skies. The flight lasted 32 minutes. Rybko tested basic handling characteristics: turns, climbs, descents, speed changes. The aircraft flew exactly like the American B-29 he'd trained in. That was the point. Perfect copy. No improvements. No modifications. Exactly what Stalin had demanded. Engineers swarmed the aircraft after landing, checking for stress cracks, loose fittings, leaks, any indication of problems. They found minor issues. A hydraulic line showed seepage. One engine ran slightly hotter than the others. An electrical connection had worked loose during flight. Nothing catastrophic. Nothing that couldn't be fixed. The flight was declared successful. Stalin scheduled a public demonstration for August 3, 1947, at the annual Tushino Aviation Day parade. Foreign military attachés would be present, American observers, British, French. This would be the Soviet Union's announcement to the world that they possessed strategic bombing capability. The parade began with familiar Soviet aircraft, fighters, ground attack planes, medium bombers. Then came 3 aircraft that made American observers freeze in shock. 3 Tu-4s flew over the crowd in formation. They looked exactly like B-29s, same wingspan, same engines, same fuselage shape, same tail configuration. American intelligence officers initially assumed these were the 3 B-29s that had landed in Soviet territory during the war. The Soviets were simply showing off captured American aircraft. It was a petty display, but not particularly concerning. Then a 4th Tu-4 appeared, flying alone behind the first 3. 4 aircraft. The Soviets had only captured 3 intact B-29s. The 4th aircraft could only mean one thing. The Soviets had reverse-engineered the B-29 and put it into production. The realization sent shockwaves through Western intelligence agencies. The Soviet Union now possessed the capability to strike targets anywhere in Europe, potentially anywhere in North America, if they established forward bases. American cities that had never faced the threat of bombing during World War II were suddenly vulnerable. The prototype Tu-4 weighed only 750 pounds more than the B-29 it was copied from, less than 1% difference despite all the material substitutions and manufacturing compromises. Tupolev's team had achieved what seemed impossible. They had duplicated one of the most complex aircraft ever built using an inferior industrial base and a fraction of the development time. By 1949, the Soviet Union had exploded its first atomic weapon. The bomb was carried by a Tu-4. Production continued until 1952. 847 Tu-4s were built in 5 years. The Soviet strategic bombing force was real. While Soviet engineers were methodically copying captured B-29s, Japanese forces faced the same aircraft under very different circumstances. From June 1944 onward, B-29s appeared in Japanese skies, with increasing frequency, first from bases in China, then from the Marianas. Finally, in crushing numbers from Guam, Saipan, and Tinian, Japanese fighter pilots, who engaged the superfortresses, reported back with disturbing observations. The American bombers flew at altitudes Japanese fighters struggled to reach. The Nakajima Ki-43, Oscar, and Mitsubishi A-6M0, Japan's frontline fighters, were optimized for maneuverability at lower altitudes. Above 25,000 feet, they became sluggish, unable to catch the B-29s flying at 30,000 feet or higher. The few fighters that could reach those altitudes, the Kawasaki Ki-45 and later the Nakajima Ki-84 Frank, discovered another problem. The B-29 crews weren't wearing oxygen masks. Japanese pilots, struggling to breathe through their own masks at maximum altitude, could see through cockpit windows that American pilots were working in shirt sleeves. The psychological impact was devastating. The Americans had technology that allowed comfortable operations at altitudes where Japanese pilots could barely function. Japanese technical intelligence officers examined wreckage from shot-down B-29s. 147 superfortresses were destroyed by Japanese fighters and anti-aircraft fire during the entire campaign. Each crash site provided opportunities to study American technology. Engineers measured armor thickness, examined gun turrets, studied engine components, collected fragments of the pressurization system. They understood what they were seeing. The circular fuselage cross-section designed to withstand internal pressure, the heavy door seals, the pressure regulators, the oxygen system that served as backup if pressurization failed. Japanese engineers had theoretical knowledge of pressurization technology. Several had studied abroad before the war. They understood the principles. What they lacked was the industrial capacity to implement those principles in production aircraft. Japan's aircraft industry in 1944 was struggling to maintain production of existing designs. Monthly airframe production had peaked at 2,541 aircraft in May 1944. But American submarines were cutting off raw material shipments from Southeast Asia. Strategic bombing was destroying supplier networks around major manufacturing centers. The earthquake that struck the Nagoya region in December 1944 further disrupted production. Japanese engineers did attempt to develop pressurized aircraft. The Tachikawa Ki-74 was a high-altitude research aircraft with a pressurized cockpit. First flight in May 1944. It was intended to test technologies for future bombers. Only one prototype was built. The Nakajima Kika, Japan's only jet aircraft to fly during the war, had its first flight on August 7, 1945, one day after Hiroshima. Too late to matter. 18 more were under construction when the war ended. The problem wasn't knowledge. Japanese engineers knew what needed to be done. They had access to German technical data sharing through the Tripartite Pact. They had examined American aircraft wreckage. They understood pressurization, turbocharging, advanced metallurgy, sophisticated fire control systems. The problem was industrial capacity and resources. Japan produced approximately 64,000 aircraft during World War II. The United States produced approximately 296,000 aircraft during the same period, nearly 5 times more. And American aircraft were generally larger, more complex, and more technologically advanced than their Japanese counterparts. Steel production told the same story. In 1941, Japanese aircraft industries had capacity to manufacture 10,000 aircraft per year. But that capacity required raw materials Japan didn't possess domestically. iron ore from Manchuria and Southeast Asia, aluminum from the same regions, rubber, oil, all transported by merchant shipping that American submarines were systematically destroying. By 1945, Japan's industrial situation was desperate. Factories built aircraft using wood substitutes for aluminum. Quality control deteriorated as experienced workers were drafted into the military. Training programs for new workers were shortened to meet production quotas. The Nakajima Ki-115 Tsurugi was designed as a kamikaze aircraft, so simple it could be built by unskilled labor using non-strategic materials. Welded steel tube fuselage, fixed landing gear, wooden wings, all to save aluminum and skilled labor for more capable aircraft. The Tu-4 fleet gave the Soviet Union strategic reach it had never possessed. Soviet long-range aviation regiments received their first Tu-4s in 1949. By 1950, more than 270 were deployed. NATO assigned the bomber the codename Bull. Intelligence analysts studied reconnaissance photographs, trying to determine exact production numbers and operational capabilities. The psychological impact exceeded the military capability. American cities that had never faced aerial bombardment suddenly had to consider the possibility. Civil defense programs expanded, radar networks were built across North America, fighter interceptor squadrons trained to engage high-altitude bombers, surface-to-air missile development accelerated, all because the Soviet Union now possessed aircraft that could potentially reach American territory. The irony was profound. American technology, copied without permission or payment, now threatened American security. The B-29s that emergency landed in Soviet territory in 1944 had enabled Soviet strategic aviation to leap forward by a decade. Without those aircraft to copy, Soviet designers would have needed years to develop equivalent capability through original research and development. The Tu-4 had significant limitations compared to its American parent. The Soviet copy was slightly heavier, the engines were less reliable, range was somewhat shorter, the fire control system was less sophisticated than the American original, but it was close enough to carry atomic weapons, close enough to reach distant targets, close enough to change the strategic balance. American strategic planners recognized they could no longer assume homeland invulnerability. The oceans that had protected the United States from European and Asian conflicts no longer provided absolute security. If the Soviets could base Tu-4s in forward locations, major American cities would be within range. Reports circulated of possible one-way missions, hundreds of Tu-4s carrying nuclear weapons, attacking American cities, the crews bailing out over neutral territory or accepting certain death. The Strategic Air Command, established in 1946, expanded rapidly. More bombers, more tankers for aerial refueling, more bases. The American nuclear arsenal grew from a handful of weapons in 1945 to over 1,000 by the mid-1950s. The logic was deterrence. If the Soviets knew that attacking the United States would result in devastating retaliation, they wouldn't attack. Mutual assured destruction became the foundation of Cold War strategy. The Tu-4 served in Soviet and Chinese air forces until the early 1960s. More advanced bombers eventually replaced it. The Tupolev Tu-16 jet bomber. The Tupolev Tu-95 turboprop bomber, which remains in service today. But the Tu-4 was the aircraft that established Soviet strategic aviation. It proved Soviet industry could produce complex, long-range aircraft. It demonstrated that the Soviet Union could compete technologically with the West, even if that competition required copying Western designs. Tupolev himself never publicly discussed the fear and pressure that drove the project. He continued designing aircraft for the Soviet Union until his death in 1972. He created the Tu-16 jet bomber, the Tu-114 supersonic bomber, the Tu-144 supersonic transport. He received multiple state honors: Hero of Socialist Labor, Lenin Prize, Stalin Prize. The fear of failure was replaced by the prestige of success. The engineers who worked on the Tu-4 project scattered throughout Soviet aviation industry. Their experience reverse engineering American technology informed Soviet design philosophy for decades. When Soviet engineers encountered Western technology they wanted to match, they had a proven methodology: acquire a sample, dismantle it completely, measure everything, reverse engineer the components, adapt to Soviet manufacturing capabilities, produce in quantity. This approach had advantages and disadvantages. It allowed rapid acquisition of proven technology. It avoided the dead ends and failed experiments that original development required. But it also meant Soviet design bureaus were always following, never leading. They could copy what already existed. They struggled to innovate beyond Western capabilities. The legacy of the Tu-4 extended far beyond the aircraft itself. It established a pattern of technology acquisition that characterized Soviet military development throughout the Cold War. Copy first, improve later. Never admit the copying. The story of the B-29 and its Soviet copy illustrates a fundamental truth about modern warfare that World War II demonstrated with brutal clarity. Industrial capacity determines outcomes. Technology matters. Training matters. Courage and fighting spirit matter. But in a prolonged conflict between industrialized nations, production capacity becomes decisive. The Boeing B-29 Superfortress cost $3 billion to develop and produce during World War II. That investment created an aircraft that could strike targets anywhere in the Pacific from bases thousands of miles away. It could fly above most enemy defenses. It could deliver conventional or nuclear weapons with unprecedented accuracy. It was the most advanced bomber in the world when it entered service, and it remained formidable for years afterward. The Soviet Union couldn't afford to spend $3 billion and 5 years developing a comparable bomber. They had neither the money nor the time. But they could copy one if they acquired the plans and a working example. Stalin's decision to reverse engineer captured B-29s instead of developing an original Soviet design was ruthlessly practical. It saved time. It avoided technical dead ends. It guaranteed results because the Americans had already solved all the difficult problems. For Japan, facing B-29 raids from June 1944 until August 1945, the aircraft represented everything they couldn't match: American industrial capacity, American technological sophistication, American resource abundance. Japanese fighters could occasionally shoot down B-29s. Japanese anti-aircraft guns could damage them. But Japan couldn't stop the strategic bombing campaign because stopping it would have required destroying the industrial base that produced the bombers. That base was in Washington, Kansas, Georgia, and Nebraska, safely beyond Japanese reach. The disparity in production numbers told the story. The United States built 3,970 B-29s between 1943 and 1946. Japan built approximately 64,000 total aircraft during the entire war. The Soviets built approximately 157,000 aircraft. The Germans built approximately 119,000. The United States alone built approximately 296,000 aircraft, nearly as many as Germany and Japan combined. Those numbers reflected underlying industrial capacity: steel production, aluminum production, machine tool availability, skilled workforce size, raw material access. The United States had all of these in abundance. Japan had shortages of all of them. The Soviet Union had capacity but had focused on ground warfare equipment until the Tu-4 project redirected resources towards strategic aviation. The engineers who examined B-29 wreckage, whether Soviet engineers carefully measuring intact aircraft or Japanese engineers studying crash sites, all reached the same conclusion. The gap between American and Axis industrial technology was enormous, not impossible to bridge, as the Soviets proved, but requiring massive investment of resources and time. For the Japanese engineers examining wreckage in 1944 and 1945, understanding the gap provided no comfort. They could see what American industry had achieved. They could measure the armor thickness, examine the pressurization seals, study the fire control computers. They could understand the engineering principles, but they couldn't replicate it because Japan's industrial base was collapsing under the weight of prolonged war, resource shortages, and strategic bombing. The B-29 raids that destroyed Japanese cities in 1945 were possible because American factories could produce bombers faster than Japanese fighters, and anti-aircraft guns could destroy them. The mathematics were unforgiving. American production exceeded Japanese production by ratios that made ultimate victory inevitable. When the Enola Gay dropped an atomic bomb on Hiroshima on August 6, 1945, the aircraft was a B-29. When Bockscar dropped the second bomb on Nagasaki 3 days later, it too was a B-29. The aircraft that had cost more to develop than the Manhattan Project became the delivery system for the weapons the Manhattan Project created. The Soviet Tu-4, that perfect copy built from captured American aircraft, carried the first Soviet atomic bomb in 1949. The technology that had helped end World War II became the foundation of Cold War deterrence, American innovation, Soviet duplication. Both served the same purpose. Both proved that in modern warfare, industrial capacity builds the tools that determine outcomes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.